Well, hello and welcome to Doc Onco Physics. Keith Onco here. Today what we want to do is take a look at the wave theory of light. And this is really just an introduction, so this is not a very long video. I have another video on diffraction, which goes into much more detail on wave theories of light. But today we just kind of want to do an introduction. So light can be seen as both a particle and a wave. And it has the components or the characteristics of each one. When we think of a particle has mass, right? It can have charge, it can have some kind of spin, and particles carry energy, right? A particle is when we think of it, it's a physical entity, right? And that the fact that it has mass is what makes it a physical entity, okay? A wave, on the other hand, has different types of characteristics. A wave has things like frequency, it has wavelength, it has amplitude, right? And we've all encountered waves before. We know what waves are, especially when we think of waves, we think of like either sound waves or the waves in water, things like that. And so waves are a little bit different than particles, in fact, quite a bit different, right? One of the key characteristics of waves is that they can add both constructively and destructively. If anybody out there has noise-canceling headphones, right? Noise-canceling headphones use the destructive quality of wave addition to present a very quiet sound or no sound to your ears, like if you're on an airplane or something like that. Waves do carry energy. Okay, if you've ever been out in the sunlight before, and the sun is millions and millions and millions of miles away, but when the sun is out and it's not blocked by clouds, you can feel the energy of the light hitting you, right? And light is a wave, right? It's got characteristics of waves. And so we want to take a look at the characteristics of waves, right, as opposed to particles, in this unit. Okay, well, back in the 1800s, a fellow by the name of Louis de Broglie proved that every object displays both particle characteristics and wave-like characteristics. In fact, this was his thesis for his doctorate. And he came up with this equation over here. And the wavelength of anything, whether it's a tennis ball or a baseball or an electron or a particle of light, a wavelength of light, all show characteristics. All right, everything shows some characteristics of a wave. Now, some things are skewed way to one side where they really just show characteristics of particles. Some things are skewed way on the other side. And so he came up with this equation that the wavelength of any object is equal to h, and h is a quantity known as Planck's constant. So it's h divided by mv. Well, mv is just the momentum of that object, okay? And so the wavelength of a particle is equal to Planck's constant divided by its momentum. Okay. So let's just look at a couple of examples here. The wavelength of a baseball moving at 22 meters per second is just going to be Planck's constant divided by the mass of the baseball times its velocity, which is going to be 2.1 times 10 to the minus 34th meters. That's a really, really, really small wavelength, and for all intents and purposes, it doesn't really act like a wave at all. But it does have that wave characteristic to it, right? It is detectable. The wavelength of an electron, however, right, is something that we actually use, right? If anyone has ever heard of or used an electron microscope, it's the wave characteristics of electrons that allow us to see very, very, very small things. So the wavelength of an electron moving at a relatively small speed, for an electron anyway, at 50,000 meters per second, would be, again, Planck's constant divided by the mass times the velocity, and that would be 15 nanometers, right? That's right in the range of wavelengths, I mean, very close to wavelengths in the electromagnetic spectrum. And the visible range in the electromagnetic spectrum is somewhere around 400 nanometers to about 700 nanometers, right? And so 15 nanometers is right in that ballpark, right? So that's why we use electrons and the wave characteristics of electrons in electron microscopes. It allows us to see very, very, very small things. So a wave can carry energy, right? And so we can determine the energy of an electromagnetic wave. And this gets into a little quantum mechanics, which we're going to get to later on in the course, right? And photons are emitted when electrons release energy by those electrons returning to their ground state. An electron really just wants to be all the time in its ground state. It's sort of sleeping state, if you will. Okay, when an electron gains energy, it's sort of unhappy being at that new energy, right? So an electron can gain energy, it would like to lose that energy. And the way that an electron loses energy is it gives off light, right? And it gives it off in photons, right? Well, we have another equation here, right? And this equation allows us to determine the energy associated with, say, a photon of light, right? Where h again is Planck's constant, E is the energy of that object, whatever it might be, in joules, and F is the frequency, the electromagnetic wave. Planck's constant again is 6.62 times 10 to the minus 34th. Okay, so let's see if we can do an example or two. Okay, what's the energy of a photon of light that has a wavelength of 500 nanometers? All right, well, C is equal to wavelength times frequency. All right, so this is our equation for, and C again stands for the velocity of light in a vacuum. We also have this equation. We have this equation here that E, the energy of a wave, is equal to h, Planck's constant, times the frequency of that object. Well, if we want to obtain the frequency, all right, we can get that, all right, using the wavelength and the fact that we know that the speed of light in a vacuum is 3 times 10 to the 8th. So 3 times 10 to the 8th meters per second, which is C, is equal to the wavelength, 500 times 10 to the minus 9th meters, times the frequency. And we get the frequency for this wavelength of light to be 6 times 10 to the 14th hertz. Okay, so frequencies of light are generally some pretty big numbers. Well, now we have the frequency. We would like to get the energy of our photon. Well, the energy is just going to be h times f, right? And so that's going to be 6.62 times 10 to the minus 34 times 6 times 10 to the 14th, right, which is our frequency. And that equals 3.972 times 10 to the minus 19th joules. Now that's a pretty small number, right? And we get a little bit tired of writing small numbers down. So a lot of times what scientists do is they will convert this energy into another form of the same thing, right? And they use something called the electron volt. Electron volts, all right, again, is just another way of saying energy, right? 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. And 1 electron volt is the energy required to move 1 electron through 1 volt. Okay, that's why it's called the electron volt. So if I want to figure out the energy now, it's just going to be 3.972 times 10 to the minus 19th joules divided by 1.6 times 10 to the minus 19th, right? And that is electron volts per joule. And what we end up with is a nice number here, 2.48 electron volts. And the ratio that we generally use here is 1 electron volt is equal to 1.6 times 10 to the minus 19th joules, as x electron volts is equal to some number of joules that you may have. And in this case, it was 3.972 times 10 to the minus 19th joules. So we just set up a proportion like this and solve it, and that's all I did down here, right? So we multiply these numbers here, then we divide by this, and we get the number of electron volts. Okay, and lastly, we just want to discuss a little bit about, and then we're going to get into diffraction in the next video, is the superposition of waves. Now this works with any type of wave, and it especially works well with electromagnetic waves. So if you recall from back in waves, right, if I take two waves and they are in sync or in phase with each other and they come into contact with each other, what's going to happen is we're going to get this thing called constructive interference, and we're going to get a larger wave. Okay, so the amplitude is going to be 2 times whatever the wavelength or the amplitude was in the individual waves, and since they're both the same amplitude to begin with, they're both in phase, they just add up and the amplitude becomes 2 times. Now, if we come down here, right, these waves are 180 degrees out of phase. Okay, and so when I have a peak amplitude over here in the positive direction, I have a peak amplitude over here in the negative direction. And if we just algebraically add up all of these amplitudes as we go on, right, what we get is, right, 0 when we add up all those waves. And this is, again, how things like noise-canceling headphones work. They take a wave coming in, it creates a waveform in the exact opposite direction, right, adds them together, and you hear nothing, which is kind of nice if you're on an airplane or somewhere that's really noisy. Okay, so this is an introduction to waves, and I hope this helps you. If you would like to see diffraction explained, there's a really good video I have out there in diffraction, so take a look at that. So I hope that helps, and have a great day.